All right, so we're in lecture 3 here. Development and risk management processes. Right, we did it. We did it, right, okay, so lecture 3, development and risk. So we're talking about now. Well, we'll talk more about risks later, but right now, what are all actions required for project management? What are all the things you have to do? So there's 2 types of things. There's, I don't know why I didn't translate it, but hulot hanihul, which means actions that the administrator of a project would take, or the person who's running the project. And then here. And then we have the field, the areas in which what he has to do with his administration. So one of them, let me see, is risks. He has to deal with risks. Risks means risks to the success of the project. Will the project succeed? What can jeopardize the possible success? That's a good word. Jeopardize the possible progress of the progress. He also has to manage the people, the scope of the project, how big of a project, what is the exact work plan, what are the milestones, how will it progress. And then he has to plan the organization. He has to have a manager for the project. There has to be a manager for hardware, software, and for the system. In other words, the environment in which they program. And then here you have planning, tracking, recording. Okay, I'm not sure if this tells you that much, but let's go on. Classic software. So there are how many? 8 or not 8, I think. Classic, software development methods. How should we develop? How do we go about planning our process and running our whole process, running our whole project? How do we run a project? And there are 8 ways here, and we're going to go through all of them. So the first one is waterfall. And waterfall, the idea of waterfall is that each stage of the development in the process development once it's complete, you go to the next stage and you don't ever revisit the previous stage. That would be the classic idea. So first you do requirements analysis. You figure out what you're supposed to do. Then you design, and there's what problem are we solving? Then the design. What is the design of our software? And then before you even write any line of code, and then the whole design is finished, and then you do implementation. You start doing the coding. And then when all the coding is finished, then you do some testing. It's obviously there's going to be some testing during the implementation. But basically, the idea is you finish all the coding, and then you do all the testing, and then you're just left with maintenance, which means, if there's updates, if you found somebody hacked your system, you got to change something, that's maintenance. And that would be the life cycle, waterfall. And the idea is that water flows in one direction down a waterfall. It doesn't flow back up. So you don't revisit the previous steps. He said there might be returns to previous steps, but overall it flows down. And the input from one step is there's an output of this step. The output of the requirements analysis allows me to now start the design. And the design allows me to now start the implementation. And once the implementation is finished, I can start the testing. And so the output of one level is the input of the next. So what are these phases? The requirements phases: explore the concept, elicit the client's requirements. I guess brainstorm about what you're going to be doing. What is the program? What does the client want? And there's also an analysis stage, which we didn't see in the previous thing here. Well, we've said requirements analysis, but here we're breaking them up into 2 parts, because this is the requirements analysis is like, I guess, deeper analysis into what the requirements are. What are his requirements? Draw up the specification document. As here is more like brainstorming. This is brainstorming, and you just sort of get the information. Here, you categorize it, analyze it, put it in a initiation document, which you made. You try to answer the question what the product is supposed to do. Draw up the software project management plan. Figure out how you're going to manage the project. Then you go to the design phase where you actually answer the question, how does the product actually accomplish what it's supposed to do? How is the software going to be written? How many classes? What is it going to do? You define how many database tables, what are the fields in each database table, all the details. And then you do like the small job of coding it. Because theoretically, the coding will become very easy if the design is very detailed. If I know exactly all the functions and what the parameters are of all the functions, and a lot of companies actually, or at least especially in the past, work that way, and programming in the past was considered like grunt work. It's considered like not the real like difficult program. You give it to a person who doesn't have much training, he just has to follow the instructions that he was given. He may not even know what his class is used for, he just writes a class with all the functions that he's told. And he's told what he's supposed to do, and he just produces it. Then once all the coding is finished, now you do all your testing, your unit testing, your integration testing, acceptance testing, and you deliver the product. And then there's still post-delivery maintenance, which means, like I said, updates, or maybe you contract and have a few number of changes that he can ask for, and you'll do that. And then retirement. Well, every project eventually ends. Every software is at a certain point not supported anymore. Some haven't yet reached that point. Okay, disadvantages and advantages of the waterfall. Advantages: simple and easy to understand and use. Right, you don't have to go back and revisit. You just do one thing, you finish it, you go on to the next thing. Easy to manage. Each step has specific deliverables and validation process. So we can decide, have we got what we need? Have we got all the things for this stage? Okay, now we can go on. So it's clear how we progress and that we are progressing. The disadvantages: it's going to take longer because designing it, you may redo the design. All these stages may take a long time, and you've done 3 stages before you've done any coding. The information system is only received at the end of the development process. Right, I don't get any kind of feedback of what I'm producing in the interim. But if I'm building a Hanukkah menorah, I start to see it take shape as it goes. Here, I just plan, and it's like I would build a Hanukkah menorah. Just first I would talk about how it should be, and then I would plan it, and then I would design it, and all this stuff, and I wouldn't have anything physically yet. Software testing is only at the end of the process, which is very weird. Because it could be that nothing works when you come to test it, and you got to go back and do everything again. It's not designed for change. No, you can change things, but it's expensive. When will we use the waterfall model in that case? I think I talked about this in the first lecture, actually. Do you remember what I talked about?
When you waterfall?
Yeah, do you remember what I said?
Is it when when it's very clear and exactly what?
Yeah, right. You know what's called the problem domain. You know the problem domain well. Also, didn't I talk about when you have bidding for a government contract? Did I talk about that? Well, the good thing about the waterfall is in the early stages we can already know how big the project is going to be. We're not going to come up with lots of changes in the middle. So we know how long it's going to take, maybe, and we know how much money it's going to cost. So we can already estimate costs from the beginning, and then we are able to participate in a bid with other companies to get a contract. If there's several companies that are all interested in the same contract, we need to say how much it's going to cost, and they might take the lowest bid. Well, we want to make an accurate bid, so we need to first plan out what we're going to do. If we do everything as we go, then we have no way of coming up with a budget in the beginning. So that's what I said then. What here it says is a little bit different. Since the waterfall model is not suitable for projects where the requirements are at a medium to high risk of change, it's not suitable for very complex projects, object-oriented projects. I don't know why that. That's what it says here. I didn't write that. I don't know what I can make a very not complex project with object-oriented. principles. But anyway, long ongoing projects, if the project is a continuous project. Like, think about the project that for Microsoft that makes the Word program. They're continuously changing and updating things. I couldn't possibly have planned 40 years ago what they did now, what they've done now. Like I just discovered that Word now has a translation feature. Where you can highlight, or you can give it text, you can just take a Hebrew text and highlight it a page and it'll translate it for you. You use that? Not really. Anyway, it's a good feature.
What? Where?
In Word,
Okay, how, but is it as good as like Google Translate?
maybe better. I don't know, I didn't compare it to, what's it called? Chat GPT.
Text is really good.
Yeah, I have to try that. So long ongoing projects are not good for it. But the waterfall is used when the requirements are well known and clear and fixed. That's what you said. Product setup is stable. As we know what the product is going to be, it's not going to change. For example, the computer that runs an airplane. The airplane is built. We're not going to add two more wings to the airplane in the middle. We're not going to change the engines. We're not going to. Maybe small things will change, but we're not going to change it in general. Built-in technology. I think it means we're using pre-built. I don't know if built-in is the right word. Maybe already built technologies. In other words, somebody off-the-shelf technology. We're going to incorporate them. So that makes it easier. No vague requirements. As the requirements are very clear. The project is short. That also I'm a little bit suspicious about that. Why short? Dafka waterfall is going to make it longer. This is when we should use it. It could be, I mean, short in the sense that it's not 40-year project like Word. Short maybe in the sense that it's like a 5-year project to make a software for a new spaceship that's going to go, to Mars. So we know we have a deadline.
If it's a long project, then with the waterfall, it'll just take so long to come out, but.
You're saying since it makes it longer, better start off with something short.
Release the code at the end of the whole process.
Right.
So it just will end up taking so long.
Right, but there are plenty of very short projects that don't use waterfall. Like that use other methods, like we'll see. Where if you want a result really quick, you wouldn't use waterfall. Waterfall is really something where you don't mind getting the result far in the future. Well, that's obvious.
If you're a software engineer, would they say, okay, we're using waterfall for this project, or you just work on it and like it'll end up being like
Why do you say that? You're asking,
as
an engineer, would I be involved with this? No, you wouldn't. As an engineer, you would come to a company and they'd already have a project running, and they would be telling you to do something, and you might not even know that it was waterfall they used, or you might not know what it is. But you might at a while figure out when they start telling you update things all the time. Then I had a company like Amdocs 15 years ago, so they or 20 years ago, they basically were using kind of waterfall where workers would come and they wouldn't know anything about the system that they're programming. They would have a little piece of it and they would program it. And it was all planned out ahead of time. And you this is really for people who already have a lot of experience programming, who are already now in the position to plan a project. In summary, this model works well for small projects where the requirements are well understood. I'm not sure I agree with that. Small, but let's say finite. I would change the word small to finite. That's a better word because as opposed to infinite. Right, they're not like Word. I consider infinite. All right, another one is the V model. Software testing throughout the development cycle. So we're testing while we develop, not just at the end. Tests will appear at several stages. Customer requirement phase, acceptance tests. So in other words, even at the beginning, we're going to have some kind of testing when we get the requirements from the customer. Analysis phase, system tests. So here, I'll show you the picture. It's going to say the same thing. Here you see a V. And the idea is that when you're gathering the requirements. You're also doing acceptance testing. What is it? Did you discuss acceptance testing in the introduction to this course, in the previous course? Do you remember? Let's take a quick look. Remind ourselves, what is acceptance testing? Except in engineering, acceptance is a test conducted to determine if the requirements, right, of a specification or contract are met. The systems engineering may involve black box testing, performing a system, for example, a piece of software. And we're not dealing with, what about software? Is there a specific section? Well, the basic idea is that it's like you check with the customer if the requirements that you got are the way you want it. You do the systems analysis and then you check, is the system working the way it should? Software design. And then you take all the different pieces of software and you integrate them and you see if they work together. So as you're going, and then only at the end you do coding. Question is, how do you do these tests if you haven't coded at all? All these tests on the right here are done before the coding. Coding is the last thing here.
Like the arrows across are,
This is time. This is at the same time.
they're doing it the same. And then at the end you code.
Yeah, that's the way I understand it. Execution of the design or accept. In other words, what's the steps? The first step is you do the requirement stage. And then you design your tests. I guess you don't run the test, but you design your test to test if the program works. You learned about extreme programming,
You think so?
where like test-driven programming, where you write the test first. So it's kind of like that. We're writing a test though for each part. So we have a requirement, so we come up with some kind of a way of testing whether the requirements meet our goals. Perform the analysis phase, so then system test design. After you do the analysis, then you do the system test. So you design the system, and then you have some kind of test to test if the system is working, or produces the outputs given the inputs, right? The tests are always given. What does it mean black box testing? It means I don't care what's going on inside, I just have a certain set of inputs. And do I get the outputs that I'm supposed to get?
So it's like waterfall, but with testing.
With testing all along.
So with waterfall, you don't test, so I feel like you need a test throughout.
Yeah, right, it's exactly. You don't test
It's so interesting, because then you're gonna get to the last stage.
and nothing
Be
works.
done, yeah.
Design your integration, perform system design phase, design the system, and then design your integration test, perform the, see, it says always design. You're not gonna actually run those tests because you don't have a system, all these are design tests. System test design, design your integration test. Perform the module design setup, then design your unit test design. Then perform the coding. Now that you've done all the coding, now you can start running the unit test, running the integration test, and you go back up the V. So you do, it is a V in the sense that you do progress through this in time. But the design of these tests is at the same time as you do each phase. So I guess it is like your tests are doing at the end. The actual tests, but you at least put the design for the tests early. Okay. A distinction must be made between writing the tests and running the tests. I don't know. This slide put that later, okay. Right, in other words, the design of the test is simultaneous with the first phase, but the running is only later. Alright, advantages, disadvantages, and use of the V model. Advantages is similar to waterfall, only here, there's an advantage that the waterfall model does not have, which is writing the test scripts at an early stage before the coding, which can help prevent mistakes and save valuable time. That is, we're not gonna wait and only start writing the test when the whole system's finished. That's kind of foolish. Like waterfall, a V model is used when we have small, medium-sized project where the requirements are well time stable. Okay. Third type, build and repair. I didn't translate that. Build and repair. This method is also called code and fix or trial and error. The initial product is being developed without any formal process or orderly work instructions. There is no pre-definition of customer needs even. There is no distinction between the stage of development. You storm the program into the product until you build it without any stages. You just start writing it. You think you know what you're gonna do, and you start doing it. And then you figure out it's wrong, and you fix it. And if you figure out it's more wrong, you fix it again. So build and repair model, or build and fix model. I guess the names are interchangeable. I think this is whatever. This is actually build and repair is the translation to Hebrew. And build and fix, I found this I found on the internet, this diagram. Because there was a Hebrew diagram and I replaced it with the English one, and he called it build and fix. Same thing. The truth is, you see here, trial and error is probably the best, or code and fix. Okay, build first version, modify until client is satisfied. So we keep, that's what this arrow here means. We keep going back and modify. Then once it's ready, we go to the maintenance phase, it's finished. But we may come back for maintenance to modify. And then eventually retirement. So the idea is that we build a version and we show it to the client as quickly as possible. And then we get feedback. Steps. Reaching users. First, as we talk out, we've reached the users, we ask them what they want. We quickly gather the needs, understand what they want. Write the code. Show the user the result. Are users satisfied? If so, go to 9, end. Otherwise, get comments and complaints and go back to 3, write the code. That's just the words of the diagram. Advantages, disadvantages. Disadvantages. We forego steps such as planning, design, analysis, testing. That can cause a major problem with the system. The system may not work. We just started coding without knowing what we're doing. When there is no structured method, it's difficult to work in a large team. Difficult evaluating deliverables. In other words, it's hard to know if I produced anything worth, maybe everything that I did is all a waste of time. I don't have anything really deliverable. Because the client's gonna say, no, it's all wrong. Difficulty with maintenance. Since we didn't design for maintenance, difficulty with maintenance. In other words, we have no design really, so it might be hard to update might be hard to change our code because we didn't think about how we're gonna change it. We just started coding. Wait a second. Advantages. Programmers love to work in this model. They don't have to work, they can just get to work right away. This is for several reasons. Psychologically, most programmers are accomplished people and therefore usually want to see immediate results. Quick implementation gives a sense of tangibility to the software. So first of all, people want to see results, and this gives results quickly. This is the way DOS was programmed by Microsoft back in the 80s. Using the build and repair model to develop a small, simple system such as a system that serves one department in the organization, a nurseries, I don't know what I mean by nursery, maybe like a kindergarten, a grocery store, some kind of small project. For the development of a large, complex system, the build and I don't know why I call it standard here, the build and repair model is not proven itself. A finance system, an airline flight reservation system. These are big systems. This is where it's not good. Now, the next type is the throwaway prototype. I like this kind of the best. The throwaway prototype. Preparing a prototype system at an early stage in order to coordinate with the customer's expectations and purpose. For example, I could just like make a graphical website. Let's say my program is for the web. And it's gonna have buttons and windows and, you know, drop down buttons with drop down windows with all kinds of possible menu choices. I can make that whole front end, let's call it front end, this the whole visual graphical way it looks, where none of the buttons do anything. I just have the buttons there. And then the user can get an idea of what I'm trying to give them. And they can say whether they like it. So you make a that's what I mean a prototype. Prototype can be sketched on paper, it could be PowerPoint, or it could be a front end software. And then a throwaway prototype that a throwaway prototype is a prototype that, after being used, is thrown away. And the construction of the real system begins from scratch. So as we build a prototype just to see if this is what we want to do. And if we don't, we'll build another different prototype. This model does not stand on its own, but is in addition to the use of another model such as waterfall. In other words, in front of, before we even start waterfall, first we'll make a prototype. Or before we start the V model, we'll make a prototype. And then we will have fewer changes later on, or even in front of the build and repair model. We can first build a prototype so we get an idea of what we're doing. Diagram of a throwaway. Start. Requirements. You still have to find out the requirements. Quick design. Build a prototype. Evaluate the prototype. Improve the prototype. If there are changes, then do a redesign. If there's no more changes, then we build the thing. Whatever, what's the number here? I don't know what the difference is. What's it? First, we figure out what the user wants. We make a prototype. I guess it's the same thing. We use the prototype. Improve the prototype. That's the same. Okay. When to use a throwaway product? A throwaway prototype model is used when the desired system interacts extensively with end users. As we really care if the users like it. And then we want to show it to them. We want to develop a system with good human-machine interface. The system is critical to the organization. All systems are critical, but we want to know how it's working with the user. We want the user to see it. I think it's always a good idea to make a prototype. It clarifies a lot. Advantages and disadvantages. Advantages: user involvement is in development. We're constantly talking to the user. I mean, in the development of the prototype. Better understanding of the system you want to develop. Right? It clarifies what you're trying to do. Early error detection. We can find mistakes quickly if we didn't do the system the way it was supposed to be done. Quick feedback from user leads to better solutions. Missing functionality can be easily identified. Well, that's actually the main thing. That's the main unique thing about it, is that we can see, oh, we're missing a certain drop-down window. Oh, we didn't know we wanted that. Only when the user actually sees the program does he realize that they forgot to mention something. Right? A lot of times the user forgets to mention what he actually wants. Disadvantages. There's a danger of descending into the method of build and repair. In other words, when we're working in the prototype, we can say, oh, I'll just, in the prototype, I'll just make this one window actually work. Because I see it's just a few lines of code. And then I'll make this one actually work. And you start, while you're doing the prototype, you start actually implementing things because you're tempted to do it because you're right there and it's just like one more line and they can get the thing working. So you do that. So now you've started to do build and repair and they can throw it all away. Perhaps. Wasting research on a model system that will not be used. Well, obviously, you're going to be wasting resources. Incomplete or inadequate problem analysis. Right? You may never really have analyzed the problem. You didn't really sit down and think about it. You just started writing. Okay. Another type, I think it's the fourth or fifth. Evolutionary prototyping. Well, the other one sounded like evolution because we said we go back and do a new design, build a prototype. Let's see. Evolutionary prototype, prototype model that evolves more and more step by step until it eventually becomes the working system itself. Now, we don't throw it away. That's the point. We don't throw it away. In evolutionary, we build a prototype and then we start filling it in. and we start changing it. Build a prototype, what's the difference? Why would you ever not do this one? Why would you ever do a throwaway? Because if well, first of all, if the throwaway is just on a, remember we said it doesn't have to be a program, it could be on paper. If you know you're never gonna use it, then you won't build it as seriously. Even the prototype, like for example. If you're building a prototype of a plane, you're never gonna fly. You could build it out of cardboard, you don't build it out of aluminum. Building a prototype with the intention of expanding and improving it until the final system is obtained. So you build a prototype, but it just means you start with the front end, and then you build the back end later. You start with the way it looks. In an involving prototype, the incomplete nature of the application may result in our not liking using the system. In other words, we may show the user a version that the early prototype that he just doesn't like, and then we say, well, okay, we'll improve it, and then we keep improving it, but we've started on the left foot. We've given him a bad impression, and he's not so enthusiastic about the project, and he may never want to use it because he saw a prototype that he didn't like. You'd rather hear that we threw it away and we started a new one. Incremental model is the sixth, I think. Incremental model. So what is the incremental model? In this model, we divide the system into parts. Each time another part is added. Suitable for a large system built from different units. Sometimes we have lots of units, and we add on to it. First, we do the most basic unit, and then we add on essentially sections of the program that improve, add functionality. For example, a financial system of enterprise consists of subsystems that are accounting, budgets, clients, staff. There may be different sections of our program. We may start with just one. We may first just do staff and then later add clients. The incremental model concept. In this model, the division into parts is known in advance. But you got to know that you're going to have all these parts, and then you can say, well, which one we do first? And the idea is to divide the system into parts so that every part can be released to the customer, and every subsequent part can be released as it becomes available. So we have, for each part, you can use a development model such as waterfall. As you're doing each part, have to have also a design and also all those steps. So we might use V or waterfall or any system, or just start build and fix. It's funny, Elon Musk has this other motto, which is break things. I mean, it's not he didn't invent it, but the idea in 10 years ago or so in Silicon Valley was you got to break things and rebuild them. It's kind of like the build and fix. It's fix and build. First type of things ruined, and then start fixing. Anyway, here's incremental. So I have an idea of building the Mona Lisa. And I know that it's going to have these different parts. So the idea is not fully thought out. It's a little vague still. And then I build the actual top. I build the left side. I build the right side. I finish. So in other words, I have an idea of the whole project. I divide it into sections, and then each section I develop piece by piece. That's what we call it incremental. Oh, I didn't find a good translation. I didn't find a redesign for this picture, so I have to leave it. Build and test initial design. There's a translation here. Yisum ubedika degem rishon. Right. So we come up with initial design. Yisum integratia ubedika bniya ikvit ad shema'arechet mushlemet. Right. This is just saying what we said before. We keep on incrementing parts and doing integration until it's ready. Then it becomes operational, and then we go to retire it. Okay. Actually, very similar to the previous diagram. Matter of fact, probably the same. Advantages and disadvantages. Releasing parts of the system. So advantages. Releasing part of the system allows the consumer to see part of the system even before development is complete. Right, we're not like pure waterfall the whole system. We get to see something right away. More flexible change because the parts are smaller, so they're easy to fix. Easier to change. Benefits of divide and conquer, separating the system into parts allows for better management of each part. Easier to find errors and better risk management. Because I really have small parts that are really separate. I can test them better, I can look for bugs better, it's easier to manage. The client can comment on any software version. In other words, we can get responses from him along the way, because we didn't wait for the whole project we finished to show it to him. We'll show him, you know, the head of Mona Lisa, and he says, no, I wanted a blonde woman, then we can start over again. We don't have to wait till we finish the whole thing. Requires meticulous planning and good design in order to achieve the correct vision of the system. In other words, if it's hard to design a system, it's even harder to design a system and figure out what the parts are. And make sure that each part is independent and can be added to the original part of the system. Requires a clear and complete definition of the entire system before unpacking into increments. Right, this is very different from the build, trial and error method, build and fix, because I have to know what I'm doing. I can't just I have to know the whole system in order to divide it. If I'm going to do parts, I have to know what the parts are. Requires consideration of integration between the parts, which makes the process more expensive compared to waterfall. Right, we have to think about how we're going to have these different independent parts communicate with each other. So that makes it more complicated than waterfall. Waterfall, I can write just one big program. When to use incremental model. This model can be used when the main requirements of the complete system are well defined. When it is necessary to bring a product to market early. In other words, to bring something to market. The point is some kind of product. New technology is in use. Why is it good for new technology is in use? I think because if new technology is in use, then we want to use that technology and make sure we understand how it works, make sure we can get it working. We'll use that technology, make sure we've got it working, get the first installment ready, and that works. So now we've mastered the new technology, now we can go on to the other parts. If we're using a new technology, we want to find like a small part of the program that we can make sure that the technology integrates with what we're doing. And then we can build, then become an expert in that new technology on one part of the system. There are some high risk features and goals. In other words, there are some things that are more risky than others, so we'll put them to the end. We'll put those to the end. Get the basic parts done. So if we know we have some very risky things, so we'll say, okay, you know, as the procrastinator says, why do today what you can put off till tomorrow? Do it later. It's high risk. Don't start with the riskiest thing. It's like if you would be Elon Musk designing SpaceX, you might first, you know, there's a rocket and there's an engine structure. You might first, I don't know, design engines. And if nothing else works, at least you got the engines working and you can sell those to other companies. Or the iterative model. That's more what we do nowadays, more iterative. So let's see. So it's the same idea, but look at the picture now. I have, what does it say? Woman in pastoral setting. So he has an idea. He wants a woman in a pastoral setting. Exactly what? So first he draws like an outline, then he draws a little bit more with some shapes, and then he fills it in. In other words, it's not that he's in part by part. He is iteratively, he's going over the whole thing over and over again. Because it is difficult to understand the whole system clearly from the beginning. So this model, you work on the system in stages, but relate to the whole system from the very beginning. But you still have stages in the sense that you know, design stage and then implementation and then fixing. At each stage, we understand more and more about the requirements and move towards the complete system as we keep getting better. The iterative model software is a cyclical process in which software is built. Gradually, the iterative development, the development of the complex parts is introduced as early as possible to reduce the risk in development. When we do the complex parts early, we don't push them off. And as opposed to the other one. because we wanna make sure, I guess, that we'll be able to do those things, so we wanna do it from the beginning. So here you see iterative and incremental. And here you can combine them, where the beginning has a vague idea, and then you decide to the vague part of one part, gets that part perfected. Then a vague part of another part, gets that part perfected, so you can do both. Okay. The spiral model. This model was proposed by a guy named Boom in 1988. The name of this model comes from its shape. Model is like a spiral with the goal of expressing iteration and rotation. In each iteration, the waterfall is used on part of the requirements. So I guess it's kind of like a combination of this, because we're doing iterative, but on parts, right? That's what he's saying here. Iterative on just the face, iterative on the hands. Again, in each iteration, the waterfall is used on the part of the requirement that we're working on. Risk analysis was added as an integral part of the model. We also do risk mitigation oriented model. We try to limit risks. Before moving on to the next stage, you do a stage of risks and costs. Now, and as you analyze how much risk and cost is the next stage going to be, and you have to make a decision whether to proceed to the next stage or not. And before you go on to the next stage, say, well, I've already produced something. Is it worth continuing? What am I going to succeed? How likely am I going to succeed? How much is it going to cost? Here's this picture. First is determine objectives. Identify and resolve risks. So you figure out what are the risks to this system. Whatever. Development and test. There's 4 quadrants. Plan the next iteration. So you see those 4 quadrants? There's four quadrants. And as we go through this spiral, we're always going from one quadrant to the other. So here, okay. Here, you see in the middle, I actually start from the middle here. Risk analysis, we do some kind of risk analysis. Figure out, is this project worth our time and money? Then we do a prototype, let's say a prototype. Then we figure out how it's gonna run. Requirements plan, life cycle plan. We come up with a plan to decide what the requirements are gonna be, how long this whole project is gonna take, life cycle. How long is this gonna take? When are we gonna finish with it? And how long are we gonna keep doing maintenance? Now this was just for the initiation document that you wrote. This is just the concept, and now we move on to again risk analysis, and we come with a better prototype. Software requirements. We think about what the software requirements are going to be. We validate the requirements. This sounds like the V plan, development plan, and then and that's all. This is planning the next iteration. Over here, say requirement plan and lifecycle plan. I was planning the next iteration. Here, development plan. How am I going to actually program it? So again, we do risk analysis. We come up with a prototype. Software product design. We actually design the software. Design, validation, and verification. So all this is development and test. It's in the quadrant of development and test. Now we go on to integration and test plan. And that's planning the next integration, because we have to figure out how we're going to do the integration. Determining objectives, alternatives, constraints, etc. We go, and then we finally do code, unit test, integration, acceptance test, implementation. So we're starting in the middle and going out. And we're going always through, we keep on doing, identify and resolve risks. We keep on doing all these different activities that are in the different quadrants. We return to them again and again as we're going through essentially the V model. So what do we write here? In each sprint, we do the following. Choose some of the requirements. First. Reduce the risks inherent in our chosen requirements. Risks means risks to the project not succeeding. What's, the first thing that comes to my mind when I say reduce risks is, let's say. Using a pre-built function if it exists. You know what I mean, if there's bubble sort, if you have to do a sort, don't write your own bubble sort, use the pre-Q sort that exists, it's a system library. Or if there's a whole section of programming that you need to get done, and then somebody else did it, use something that's already out there. That would reduce risks of my thing succeeding, because now I've already got part of it, it's already working. Build a small prototype that meets these requirements. According to the customer's comments, we fix what needs to be corrected. And then waterfall analysis, design, and coding. So we do analysis, so once we've got the prototype, then analysis, design, and coding, and then go back to section 1. Do another section. This is our spiraling. And these stages are the 4 quadrants, basically. Slowly we increase the product in those red. So it's also well, it's not, is it more like incremental or more like it's more like iterative than incremental. You don't necessarily know where we're going. The spiral model divides the software development process into 4 quadrants. That's what we said. Planning, risk. Planning is the upper left-hand corner, then risk analysis, engineering, and customer evaluation. Yeah, evaluation. Okay. All right, here I just explain what each quadrant. I think I already explained it. The X and Y axes. Shouldn't that be spelled with an I? Axes.
I think that's really right. How is this?
Here's with an I. Here's the E.
Oh yeah, I have eyes, right?
Yeah.
That's axis, like an axe.
The X and Y axis. The X axis is called the go, no go. Y, let's go back. This is X. Everything's no, well, let's see, why does it go no go? Because every time we reach this stage, the client can choose to stop or continue the project. When do you reach the X-axis? After the risk analysis stage. And after the user evaluation stage, right? Let's see, when do you, let's go back. Here is the risk analysis stage, identify and resolve risks. So then you come, when you finish that stage, you come to the X-axis. And after the, you also come to the X-axis after the plan the next iteration. So after the risk analysis stage, if the risk is too great, the customer can withdraw from further development. After the user evaluation phase, if the customer is satisfied with what has been developed so far, he can withdraw from further development of the project. And there's 2 possibilities, either it's too risky or he's got what he wants. In other words, over here. You don't have to plan the next phase. Really, when you hit this axis, and after you did the implementation, then you can decide whether to go to this axis or not. In other words, I can decide, am I gonna plan the next, I mean, really here is the planning, but. I can decide whether or not to do this one. If I forgot what I wanted, then I'm done. I don't have to go plan the next phase. The y-axis is called the cumulative cost because the more rounds there are, the higher the cost. So every time you pass. As the y-axis, as you go higher up here, you're doing more and more stages, it's costing you more. That's true here, as you go more and more out this way. Okay. Advantages, disadvantages. Advantages, a lot of small code deliveries to the entrepreneur, which allows the entrepreneur to check that everything is working as required. In other words, at each stage, the person who ordered this code can check if he likes it. Careful progress towards the result through customer involvement in product development by examining it, right? The customer is involved all the time. Risk management, we also have this risk management idea. We have early identification of problems. We're already doing, again, we're gonna talk about more risk analysis in the rest of the slides. But risk analysis is very important to see how risky is this project. Risk is obviously, we don't wanna put a lot of money in and then not get anything. We want it to succeed. Disadvantages, the spiral model requires experienced developers, there aren't many developers who are good at risk management either. In other words, it's hard to determine, you need good developers who are good at developing and are good at risk management. For each iteration, we may make changes to what we do. It is difficult to adjust contractual obligations when the customer pays and how much, because the amount of rounds is not known in advance. How are we gonna tell how much it's gonna cost? We don't know when we're gonna stop, because if we're doing risk analysis all the time, then that means at any moment we may say it was too risky, let's stop. Color change. Okay, when is the spiral model used? Suitable for a large project, suitable, why suitable for a large project? I guess if it's very small, there's not gonna be many stages, you can just plan it out and you're done. So here, it's good when we have lots of parts. Suitable for a project's requirements at the beginning are not entirely clear. That's why we have a prototype is built inside, in other words, in the project, we include the idea of a prototype too, which helps. Why do we build prototypes? Why does anybody build prototypes? Airplane, most things. It's just to make sure that we all understand what we're doing. So if things are not clear, then we don't want to build a prototype. It's also good when there are many risks. We want to constantly check. Are we breaching the amount of risk that we want to take? Alright, so what is risk management? So it's that same picture we saw in the beginning, here I did translate it. Management actions, areas of management. Okay, and here you see that risks is there. What is risk? So these slides with the little red star here are ones that I added to the official slides, based on some other things that I was done. And then what I wanted to clarify. Risk is the possibility of loss. What kind of loss? Project failure, delivering a faulty product, or project delay. Right, I don't know, there might be other failures, but these are all losses. The project is not working out right. Risk associated with, wait, when did we started at 10:30. 11:30, 12, so okay, we'll finish. Risk associated with uncertainty and loss. Uncertainty. The degree of certainty about whether the risk will occur. Now, first of all, the risk may or may not happen, the damage may or may not happen. And then the question is, how big is that damage? If the risk becomes reality, the consequences are undesirable, or the loss will losses will occur. In other words, you actually, if you think about it, if you multiply these two together, how likely is it that, let's say it's only 1% likely to happen, but the payment is gonna be $1 million. So how do I evaluate that? So it's 1% times 1 million. And it's a 1% chance that $1 million will happen. It's true that we actually have to pay the $1 million, but right now I can give it a cost of 1% of $1 million, it would be 10,000. The rationale for this, risks are out there. If you don't plan for them and prioritize them, your project will be affected out of your control. Be proactive. In other words, things might happen, think about it and decide ahead of time what you're gonna do. Detecting risk at the production stage can be expensive. Hence, risk analysis during testing is ideal for understanding what might go wrong before entering actual production. Prepare the cure before the blow. We said in Hebrew, you know that Hebrew expression?
No.
Makdim et trufa l'makat. They say why in the Talmud is a joke. Why is the section of the Talmud dealing with gittin, with gets, before kiddushin? marriage. Usually you first get married
Um,
and then you get divorced. Why is divorce before the discussion of marriage? The answer is l'academia trufa the maka. That's how do you say it?
where?
A black humor there. First have the cure before you get into trouble. Okay, the project manager in the early stage of the project must prepare a list of risks and attach each of them to each of them a way of coping with it. Because think about the risks and think what we do. It's you know what it's called, contingency planning. That's the term I should put there. I should put that in there. Remember that, contingency planning. There was another term that I had before that I wanted to add. You're not taking notes, are you?
You said,
Wait, like an hour
I'm
ago.
not taking notes on every word,
You're not writing every word I say?
not every single word.
There was another thing that I wanted to change in the translation, but okay. In the beginning,
With the, what was it, the fix and
trial and error, yeah.
trial and error,
Yeah, I wanted to fix that. Yeah. Okay, there's not, there's even one, okay.
repair,
What?
was it the repair and fix or no?
Yeah, well, he called it, in one of the pictures, he had an official name, yeah, I'll fix that too, okay. So contingent, that was a translation, contingency planning. I should. Write that down. It's always good to use terms that are known. Contingency planning. Okay. Project risks. Every project manager should take into account of all the risks associated with the project, otherwise the risk can cause the project to have extra time, extra money, poor product quality, project failure. So let's repeat what I said. Okay, software risk analysis. Identify the risks in applications, prioritize them. Prioritize them for testing. In other words, figure out which risks you want are more important for you to deal with. Identify all potential risks and then quantify their severity, which ones are worse. By identifying possible software flaws, developers can find solutions to address them and reduce the overall risk. Causes of risks to project success. There are unexpected and expected. Unexpected, for example, really we should start with expected. Expected risks are what? The time you allocate for testing. There's the fact that you do testing means that you know that there's gonna be problems. And why do you allocate zero time to it? You could do the zero time. Oh, but I know that there's risks. I know the likelihood that things will go wrong. So those are expected risks. In complex or large applications, flaws can occur. I'm not sure what that means, but obviously there can always be flaws. I guess flaws in the design. An urgent need for the client to complete the project. So I know that I can't just keep running the clock. I gotta finish this at a deadline. So that's a risk. These are expected risks. Maybe I won't be able to finish it in time and then I won't get paid.
So this is basically just planning for the risk,
Yes,
but that takes up time and the risk might not happen, so wouldn't it be better to just, if it comes up, then take that time?
well, so we're taking the opposite approach. That's what we said here. We prepare we bring the cure before the blow.
You might be cured, then you don't even need it.
Exactly. Yes. Yes, exactly. This is a waste of time in most cases, just like insurance.
Yeah.
You pay your insurance for your car, most of the, they say you're happy that you'll never collect it. Because you don't wanna damage your car, if you have to. The requirements are unsatisfactory. We know that it's likely that the requirements are gonna be wrong, so these are expected risks. We know that we may have to, that our requirements may be not good. What are unexpected ones? Schedule delays, some kind of delay, maybe there's a war all of a sudden in the middle. Wrong cost estimates, we estimated the cost, but we made a mistake, we didn't think we made a mistake, we tried to do it right. Lack of resources, everybody quits. Half our team finds jobs in other countries. So we don't have resources. Security risks, we get hacked. These are things we didn't expect that, we didn't plan, but maybe we should plan for that. And what we're saying here is we gotta plan for both of these kind of risks. Even if people would quit, we gotta think about how we're gonna deal with it. And now another way of categorizing risks, which I call scenarios for risk occurrence. What are the scenarios? So there's unknown unknowns, and there's known knowns, and then there's known unknowns. Sounds like philosophy here. What are unknown unknowns? These are technology related risks entirely unknown to the organization. Risks that the organization doesn't know about. They're unknown unknowns. The risks generally arise from working with an unknown tool or technology. In other words, we decide we're gonna use this new technology and we think it works, but maybe it doesn't work. Maybe it brings with it a whole bunch of problems. We didn't even know about it. We didn't know what this technology is. We have no way of knowing what the risks are gonna be associated with this new thing because it's a new thing. Those are unknown unknowns. We don't know what these unknowns are gonna be. What are known knowns? The order should be. This one should be last, unknown unknowns. Fix that. Known knowns are. These risks are factual and well known to the team. For instance, a lack of development rate causes a risk of delay in software. Well, that's what I mentioned. These risks are identified early and documented in the project management. In other words, we may even put in our contract, assume we only contract that will finish at this time if we can get suitable workers and the visas are not canceled by the new president. And then we know about this risk. We know that our workers might disappear. Known unknowns. So what is this? Known, but it's unknown. But we know that we have this unknown. The company is aware of the risk, yet they are unsure whether such risk exists in the project. We know there's a risk like this, but we don't know if it's here. For instance, a miscommunication between the client and the project team can result in capturing misinformation. In other words, that's really badly written. It should be miscapturing, whatever, capturing misinformation. In other words, we have misinformation. We got from the client. We know that the information that the client expressed to us could be wrong. Could be that he told us he made a mistake. We know that it's possible that our analysis of what he said could be mistaken. Again, this is a known fact. However, whether the client has communicated the correct information or incorrect information is unknown to the team. As we're going to work with the information that we gave us, but it could be wrong. So this is a known unknown. We know that we could be wrong about this information. Okay, types of software risk. Schedule risk, budget risk, operational risk, technical risk. So schedule risks are time related. Because project can run behind schedule. Budget risks, we might run over the budget. Operational risks, procedural risks that occur in day-to-day operation throughout project development due to poor process implementation. We may waste time, we may spend too much time in meetings, we may redesign things all the time. Technical risk, the software application's functionality or performance isn't correct. Right, we thought this software did, we bought this package to help us, and it turns out it's broken. Other types of risk, people risk related to people in the development team. We have a crappy team. Tool risks, oh, I said that already. Estimation risk related to inaccuracy of estimates. Technology risks are related to the use of hardware. Organizational risks are related to, skip that. Risk management, reduce. So there's 3 things you could do to deal with risk. One is reduce the risk. Planning to reduce the loss caused by risk. For instance, planning to hire new employees to replace employees serving notice. In other words, we'll have a whole plan of how we get new employees, or we may even employ extra people as backup in case somebody quits. Transfer the risk, buying insurance or hiring a third-party organization to solve challenging and harmful risks. So we could buy insurance, we could buy like contract insurance. If we don't meet our contract, this company will pay us money. Avoid the risk, implementing strategies such as incentivizing underpaid, hardworking engineers who might quit the organization. Just pay them more, or incentivize, give them stock options if they finish the project on time, or more money if they finish it early. And then that will help avoid the risk. Now, more examples of risks. Well, you see here, for example, the team's insufficient skill in using the tools of the development environment. Maybe the people are not well trained. That's people. Use of new technology unknown to the company, new algorithms being required. And if once we're using anything new, then it introduces risk. A new customer, this guy we never talked to before. And so we don't understand the way he talks. We think when he says something, he really means it. He really is just fantasizing. We have to know who we're dealing with. These are all different kinds of incorrect evaluation of the clock. Clock stands for 1,000 lines of code. K is 1,000, and LOC is lines of code.
Oh.
So we thought that it was gonna be 10,000 lines of code, but it's really 100,000 lines. Reuse is smaller than planned. We thought we could reuse software that we'd already written for another project, but it turns out we have to rewrite everything. Types of risk and level of impact. Performance risk, cost risk, support risk, schedule risk. So does the risk affect the system performance? The actual product won't work correctly. Is the risk a cost risk? Is the cost of the project will not be, it'll cause the cost to go up. Support risk. We have a risk of creating software that'll be hard to support. Schedule risk. Is this gonna cause a delay in the project? Okay, severity of risk. Regarding a project costing $10 million. We can say that level 1 is catastrophic, it's more than $500,000, and level 4 is less than $1,000, and critical and marginal are between. So we can make a risk table. The product team identifies all risks and puts them into no particular order. The record's in a table called a risk table. Here's a risk table. A whole bunch of risks, larger number of users than planned, less reuse than planned. And we put a probability to it and we give an impact to it. Is it critical? 2 would be critical, 1 is catastrophic. Okay, so we make this table, we write the probability of the impact and the RMM. What is RMM? A plan for each risk case, what we're gonna do in case of that risk. It's left out here, but it would actually be like what we're gonna do because of this, because a large number of users than planned, what will we do if in that case? What if we plan for 10,000 users, but in the end it's gonna be 1 million users, they change it, they don't know we need for 1 million users, so what will we, even though we're not writing it for 10 million users, we're writing it to a system to work up with 10,000. But we should plan what we'll do if the customer, if it changes for some reason. We'll come up with a plan here. Risk table. Sorting the table. After we have a risk table that compiles a list of all the risks, we sort the table according to probability, and then inside of probability according to impact. So in other words, things that have a higher probability will be first, and then in those, all the ones that are 80, let's say, we'll sort them by severity. The purpose of this classification is to concentrate on the biggest risks at the top of the table. Determination of a cutoff line. So we have to set a cutoff line. Everything above the line will be taken care of, and everything below the line will no. That's what you were saying. Maybe we're waste our time on thinking about risks. If it's only a 5% chance of happening, maybe just ignore it. So what does RIM stand? RMM, risk mitigation, monitoring, and management. How can I reduce? So that's the last part of the table. How are we doing for us time? We still have.
And at 12?
I think so. If it starts at 10:30, it's an hour and a half, so that'll be 12.
Would you have the lab part today?
And we have the lab.
Oh, so that starts out after, right?
That starts after that, yeah.
Okay.
Now let's continue. So this RMM thing is how do I reduce the risk? Reduce the riskiness of the risk. And there's how bad will the risk be if, what does it mean riskiness of the risk?
Like how risky it is.
Like maybe it means the danger of the risk. I do know how to translate that. I translate.
Reduce the riskiness.
Maybe reduce.
Amount of risk, reduce the amount of risk.
Yeah, I guess.
Reduce the risk.
Reducing the prevalence of the risk. How likely it is, I guess. Use of means, legal, organizational, financial, and insurance. So first I can reduce, I think it really what I should say is reduce the severity of it, reduce the likelihood of it. And then if I can't, if those two things, in addition, the third thing I can do is pay for insurance. Risk monitoring, monitoring and updating the risk, and there's always checking, is this risk going on? You know, double check with the people, are you planning on quitting? They'll ask that every morning, are you planning on quitting? And so then I'll know how likely this happen. Risk managing. What can you do if the risk does happen? How can you escape it? So in other words, research, can I find workers in India who will be willing to work on an hourly basis if people are on maternity leave or something. The RIM program is written in a booklet is writing a booklet about all the risks. So you have to write like a whole explanation of what I'm gonna do for each risk. Here's an example. Where I write this. Project risk table, I have the table. Then I have my RIM, what am I gonna do for each thing? Okay, I read a whole book of this. Chapter 4, there's another, chapter 4 and 5 here. What are those? That's maybe less clear. 4 deals with the following: set a risk monitoring schedule once a month or every 2 weeks, recheck my risks. And 5 is each document ends with a chapter of summary. Okay. So here's like the details of this book that I would write. A description of all the risks above the cutoff, and I gotta write a description of all the risks above the cutoff line. Factors influencing the probability and impact of the risk. What are in other words, a thing that might cause me to lose workers is there gonna be a war? Are a lot of my employees females, and therefore they might get pregnant, married women, maybe they're gonna get pregnant and take paternity leave, so all those are factors that affect the risk of losing employees, for example. All right, that's it. We did.
Factor?